Thank you very much. And thanks for giving me this opportunity to present my work. So yeah, so the title of my talk is Implementation of General Quantum Measurements Using Only a Single Ancillary Qubit and Post-Elections. So this work is ongoing, yeah, finished, just finished work with Philip Maciejewski and Mihail Osmaniak. Right, so I'll begin the presentation. So measurements in quantum mechanics, if you have a quantum state and you want to extract some information out of it, you have to perform some measurement on this state. Now, this measurement is a probabilistic event, and the probabilities of the various outcomes, these are given by Born's rule. Okay, now creative application of these measurements, they give rise to applications like quantum computation, communication metrology, tomography, etc. Next. So let's describe what the most general quantum measurement, what it looks like. The most general quantum measurement is also known as valued measure, POVM. So we assume that our system is of, our principal system is of dimension D. Okay. So the most general quantum measurement is described via Naimark's dilation theorem. So what is Naimark's dilation theorem? It says that this most general quantum measurement requires you to take your principal system and attach some ancillary systems to it. Now, in quantum computation, typically we use qubits, right? So you attach various qubits as ancillaries to your principal system. This entire thing forms a composite system, and you probe that. That is, you perform a measurement of that. That will have some measurement outcomes, okay, each with various probabilities. And this entire process is describable only on your principal system. So how do you describe it? Well, you describe it using D by D matrices, M subscript 1, M subscript 2, so on and so forth, each of which is Hermitian and has positive or has non-negative eigenvalues. And these guys, they sum to identity. Okay, so this is your most general quantum measurement. Okay, now we would like to use these quantum measurements creatively in various different ways. So you can implement various different measurements by attaching more and more ancillary systems, ancillary qubits to your principal system. Okay, so if you don't attach any ancillary qubit, what you end up performing is just a projective measurement. So earlier you saw the slides of those. So these are known as the measurement effects. Okay, so so in the case when you don't attach any ancillary system and directly probe your system, directly perform measurement on your system, you would perform a projective measurement in which the effects will have this additional property. Okay, some set of measurements that you can perform. Now, if you attach one ancillary qubit and you then perform a measurement on your composite system, you enlarge the set of measurements that you perform. Okay, and so on and so forth. The most general quantum measurements you can perform if you add log D number of ancillary qubits to your system. So that is, your ancillary system is of dimension D. Okay, so your composite system is of dimension D square, and you perform a measurement on that. So typically, the more number of ancillary qubits you attach to your system, the harder it is to control everything, control the composite system, and perform a measurement of that, so your measurement starts becoming more and more noisy. Okay, so this is a problem. Okay, so what is the goal that we have set for ourselves? So we would like to implement any general quantum measurement, yet at the same time we want to reduce resources. Okay, so what are the resources that we have at disposal? So in the previous slide, you saw these ancillary qubits that you can attach. Okay, these are your quantum resources, and as I mentioned, the more of these resources you use, the noisier your implemented measurement becomes. Okay, the other resources that you have are classical resources. Okay, now we assume that these classical resources, they are free. You can use as much of these, and you can use as varied as possible different types of these, so on and so forth. They have no cost. We assume that, okay, for this work. So what are the classical resources at our disposal? Randomization and post-processing. So I will explain these in the next two slides. Okay, so first I explain randomization. So in randomization, what will happen is that you have originally two POVMs, okay, big N, this guy over here, and big N. Okay, so you can randomize them with probabilities Q and 1 minus Q and perform either of them. Okay, so you perform big N with probability Q and perform big N with probability 1 minus Q on your system. So randomization is only this part of the diagram over here. Okay, when you randomize, what you end up doing is you perform another measurement, that is big L, which is just a convex oh, this should be Q and 1 minus Q, sorry. Yeah, so big L, which is a convex sum of this M and this big N. Okay, and the measurement effects are related to the measurement effects of M and N in this way. Okay, so now from this you can see that the set of all POVMs, the set of all measurement, this is a convex set. Okay, so you can take any of them, any number of them, and you can take a convex sum of them. The result will always be the result will also be a measurement, a valid bona fide measurement. Okay, so a convex set will typically have extremal points. Okay, so you have extremal measurements corresponding to these points, and these are points basically which cannot be decomposed into convex sum of other measurements. And an extremal POVM has at most d square outcomes in dimension d. Okay, that explains randomization, and that is just this part of the figure. Now the next part of the figure comes here. Okay, so right, so your original POVM, that is this L, that is the convex sum of these guys. Okay, you can coarse grain over the measurement outcomes of L. Okay, so over here you see that this entire thing, this is L. So you have various measurement outcomes from these, and then you coarse grain over these guys. And what you get after this coarse graining, that is another POVM that is called Q of L. Okay, so this operation you can also perform. This is known as post-processing. So these are the two classical resources that you have at your disposal: randomization and post-processing, and they are free. Okay, so we just saw that any measurement is a classical combination of rank 1 measurements. Okay, okay, so sorry. Yeah, it is easy to see. It is a very simple job to see that any measurement can be written as, can be realized as a classical combination of rank 1 measurements. Okay, and these classical combination that involves randomization and post-processing, and this randomization and post-processing, that bears no cost. Okay, we assume that they're completely free operations. Right, so we can assume that the POVMs that we are interested in, okay, these are rank 1 and have at most d square outcomes. Okay, so the POVMs that we are interested in implementing, they will take this form. So big M is your POVM, and these are your measurement effects, these M subscript little I that you saw in the earlier slides. Okay, so psi1, psi2, dot, dot, psi subscript d square. All of these guys are states on your quantum system, pure states on your quantum system. And alpha I are just coefficients, which are non-negative coefficients, which sum to the dimension of your total system. Okay, so this is, yeah, right. This is the completeness property of the POVM.
But sorry, but you have to assume also something about the states, psi, yes? Or you assume they're orthogonal or no?
So the states would have to satisfy. So the sum of this alpha I psi I. So your alpha I psi are just these M subscript J's. So you just substitute the the alpha I psi over here, okay, and they have to satisfy this equation. They have to sum to the identity.
Yes, but then automatically this condition on sum of alpha summing to D will be also satisfied.
Right.
Yeah, so okay.
Yeah, then, yeah, this comes from there. Right.
Okay.
Okay. Okay, so now there is something else that we can also do. Okay, so that is you perform a measure, this is known as post-selection. So you perform a measurement and then you neglect certain measurement outcomes. That is the notion of post-selection. Okay, but so there is a notion of simulation by post-selection. So simulating a measurement by post-selection. So what is that? So let's assume that we have various measurements n subscript little I at our disposal. Okay, so we can implement these guys. Okay, we have the power to implement these guys, and let big M be some other POVM. Okay, and this big M is related to these n i's in the following way. There exists some probabilities pi such that you can take a convex sum of these n i's. Okay, and then you get a measurement over here. Now, what is this measurement? This measurement is a convex sum of this M with another measurement whose only outcome is the identity. Okay, and if you assume that this big M measurement is has little m number of outcomes, then the measurement that you get over here, this is little m plus 1. Okay, so the final outcome in this expression over here is 0, and the final outcome in this expression is just the identity. And you have a convex sum between this measurement over here and this measurement over here. So again, to repeat, you have some big, so you have these ni's, so these measurements, and there exists some way of combining them using randomization and post-processing such that you end up implementing this measurement, okay, which is related to your original measurement. If this is true, then you can simulate this big M by implementing these ni's, performing randomization, post-processing, and post-selection. Okay, so what is the post-selection over here? You neglect the final measurement outcome. Okay, so this measurement over here gets implemented, and this is the final outcome. So whenever you get the whenever your outcome, this thing your measurement device, like when you get the m plus 1th outcome, the final outcome, you just neglect that. Okay, and that final outcome will always occur with the probability of 1 minus q. Okay, for any state. Okay, and hence you end up implementing this big M. Okay, and this entire process, simulation by post-selection, has a success probability of q. This q over here. Right. So what is our strategy? Our strategy is that, okay, so we have some target measurement that we want to implement. Okay, and it has this form over here. For this measurement, we want to find some sets of other measurement which we can combine in a using some classical combination technique, randomization and post-processing, such that the resulting measurement, when we post-select on that resulting measurement, we end up implementing this M. Okay, so again, so what are the resources at our disposal? Classical randomization, post-processing, and ancillary qubits. So let's start with no ancillary qubits. Okay, so let's assume that we don't want to implement any, we don't want to use any ancillary qubits. Okay, the least noisy operation that you can perform. So firstly, is this possible? The answer is for any measurement n, any measurement of this form n. The answer is yes. So in an earlier work, simulating all quantum measurements using only projective measurements and post-selection by Mihail Osmaniak, Philip, and Zig Puchala, this was published last year in PI. They found that any measurement of this form, this can be implemented using the scheme that is given over here. Okay, so, and the success probability of implementing this scheme, that is 1 by d. So d is the dimension of your principal system, and this is the success probability. So the thing is that as the dimension of your system starts to climb, the success probability of this scheme, this goes to 0. Okay, so that is undesirable. You would want something better than this. So the question is, can you do something better than this? Okay, so this is what we consider in this work. In this work, what we do is we allow for attaching one additional ancillary system, ancillary qubit to our d-dimensional system. Okay, and this is your candidate POVM. The POVM effects, the measurement operators are given over here. So what we want to do is we want to find these smaller POVM n subscript little j. Okay, and we want to see if there is a way of combining these measurements such that we can implement the original measurement big M by a post-selection. Okay, so we find that we can do that. Okay, so you take any measurement M of this form, and you will be able to find some smaller POVMs such that if you can implement these smaller POVMs, you can implement these smaller POVMs with just one additional ancillary system. Okay, and you combine them classically using randomization and post-processing, and you can implement this M via post-selection. Okay, so let's look at the strategy. What is the strategy? The strategy is you choose some partitioning of the set of outcomes, that is 1, 2, 3 up to d squared, into subsets of d. Okay, now for illustration, I will illustrate it with one particular choice of partitioning. So, this partitioning has, like, the first subset is up 1 to d, the second subset is d plus 1 up to 2d, so on and so forth. So we construct POVMs for each of these subsets in this partition. Okay, so you get n1 over here. So n1 is, so how does one construct these POVMs? Well, you have this subset 1, 2, 3 up to d. You take the POVM effects from M, okay, corresponding to these indices, alpha 1 psi 1, alpha 2 psi 2, up to the dth effect. Okay, so you put them over here, and then you add an additional final outcome. Okay, so this final outcome would have to be such that the sum of all of these guys, all of the POVM effects is the identity. So the final outcome will be of this form. And lambda 1 is a normalization constant that you choose in such a way so that this final effect has some desirable property. Basically, it has to be of rank d minus 1. Okay, so this is how you obtain a POVM n subscript 1.
Sorry, Tanmay, I just, so it's like that because you want this last operator to be just positive, semi-definite, right?
Yeah.
And yeah, so it's like a norm of a like coarse-grained effect of a POVM when you sum over those the effects. I mean, it's some important object that will appear later.
Yeah.
Sorry, so one more question. So you can you repeat once again? So you start with a POVM M.
Right.
And how many outcomes you have in this M POVM?
So in this big M, you have at most d squared outcomes.
Okay, but why do you start from d squared? Just okay, to be the most general, yes?
Yeah, to be the most general. So the most general quantum measurement can always be written as a classical combination in post-processing of at most d squared outcome POVMs.
Okay.
D squared outcome rank 1 POVMs. So that is why, and because we assume that these are free operations, you only worry about implementing these M's with rank 1 POVMs, and these are of size at most d squared outcomes. Right. So okay, so you have defined your first measurement n subscript 1. Then you can define second, like using the second set, okay, d plus 1, d plus 2, so on and so forth. You define n2, and so on and so forth. Okay, so next question is that now we have these n1, n2, so on and so forth, these measurements. Is there a probability such that you use randomization and post-processing to combine them in such a way that you can do what you want it to do? The answer is yes. So you have a probability that is given over here. So the lambda i's that you see over here, these are the same lambda i's that you see over here. Okay, and these you can combine into a probability. And then you combine these ni's with this probability, you get essentially what you were targeting. That is a convex sum of the measurement that you were targeting and just the identity measurement as the last measurement outcome. Okay, right. So, okay, so you can do it, okay, for any measurement. Okay, so that is taken care of. Next point is, as I mentioned, you can choose different partitions, okay, of your set of of the measurement outcomes, and these will give you different values of the success probability. Okay, and choosing the right partition is important because you could choose a partition in which the value of the success probability isn't very good, but there may be another partition where the value of success probability is good enough for your purpose. So choosing the right partition is pretty important. Okay, but for the purpose of illustration in this presentation, I'm using one particular partition that you've seen which one that is. Right. So, right. So I've already mentioned that n can be simulated using these ni's using post-selection, and you get some success probability. And the resources that we have used are classical resources, randomization and post-processing. And now, there's also the quantum resource. Okay, so we said that we want to implement these guys with only one additional ancillary qubit. So this measurement operator has, so the thing is that we have constrained ourselves in such a that we can implement these njs on a global system which is of dimension 2 times d minus 1. Okay, so our original principal system was of dimension d. If we attach an ancillary qubit, our total system becomes of dimension 2 times d. So we can perform this, and we can perform these measurement n subscript 1, n subscript 2, so on and so forth. Okay, so
sorry, Tanmay,
ancillary qubit and these classical resources.
So Tanmay, can I ask you something? So this NJ.
Yeah, sure.
This NJ operators, they
right.
have how many outcomes? D plus 1 or?
So each of these has they have outcomes d plus 1.
Okay, d plus 1 outcomes. Okay. Mm-hmm.
Right.
And importantly, they have like just d out of those outcomes. They are rank 1, and only the last effect is high rank.
Yes.
That's
okay.
why.
Okay, but still they are not projective yet. Yes, I mean they're just they're not projective yet. Okay.
No. So if they were projective, then you don't need an ancillary system to implement that particular measurement. So, right.
I mean, we would like them to be projective ultimately, or modified, sure. But we are not there yet.
Yeah. So, so we are not there, and also, right. Okay. Right. So fine. Now, what we would like, okay, so what I'll explain over here is I want to obtain a representation of this success probability that you saw in the previous slides. So how do I do that? Well, you take your original measurement, M, okay, it has D square outcomes. You take, so you take the states, corresponding to these D outcomes, okay, and then you arrange them as columns of a D by D square matrix, okay. So look, these state vectors, these state vectors, they live in a D-dimensional space. That is our principal system. So in any basis, they would have a representation as a D-length column, right? So you choose some basis, and then you can arrange them in this fashion, and you get a D by D square matrix that we'll call big U. Okay. Now this big U it's an isometry. It has this property that U right multiplied by its adjoint is just the identity. Okay, so this is the same the property that these measurement operators, sorry, the measurement effects, they sum to be identical. That is the same condition that you have over here in just a different form. Now, corresponding to the partition which I use for the purpose of this illustration, you can partition the columns of these matrices into different blocks, submatrix blocks. Okay, so U1, U2, dot, dot, up to U subscript little d. So each of these U1, U2, dot, 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 U subscript little d, they are d by d matrices. And that you see over here, U right multiplied by U dagger is equal to identity. That is represented by this over here. Okay, so an alternate success probability is given by this. Okay, so these UJs are these various submatrices that you see over here. Okay, so you take a, so what is this, what is this quantity that you see? So forget square factor. So this is just the operator norm of your U. You take the largest singular value of UJ, okay, that UJ, and then you square it, that over here. Then you sum over all J's from 1 to D, take its reciprocal, and that's precisely your success probability. Okay. Now, as I mentioned again, like, you can use different partitions, and these different partitions would give you different choices of, these blocks of matrices, and, corresponding to different partitions, you get different value of the success probability. Okay. Now, long story short, what is our goal? We want to study how the success probability varies as the dimension increases. Remember that in the earlier work where you did not allow for an ancillary qubit to be used, okay, where you only perform projective measurement, the success probability for the measurements that we are studying over here, that would always be at most 1 by d. Okay, so we want to see that if you allow for an ancillary system and same classical resources, can you do better? Okay, so you want to study how the success probability varies as the dimension increases. But how do you do that? Well, a simple convert your measurement m into a random variable. Okay, so then your success probability also becomes a random variable. And then you can study how the success probability varies as a function of d. So how do you convert your measurement m into a random variable? Well, in the previous slide, we saw that, corresponding to m, you find a d by d square isometry. The converse is also true, that if you take some d by d square isometry, and corresponding to that, you will find a measurement of the form m that we have been considering so far. Okay, that is rank 1 with d square outcomes. Okay, so this we can use. Now we define, we get precisely to what are random POVMs they look like. So this will be about hard random POVM. So what is a hard random POVM? How do you get there? So you have your, so again, so you start with your original principal dimensional system, sorry, principal system, which is d-dimensional. You add to it a copy of your principal system that is also of dimension d. Your global system now becomes of dimension d square. Okay, so upon this d square dimensional system, you perform a rotation u. Okay, that's a rotation u, and this rotation is chosen with the Haar probability measure from the d square from the unitary group for d square dimensions. Okay, so this Haar probability measure, it's a rotationally invariant measure on this unitary group. Okay, so rotated it, you perform a measurement in any choice of basis. So you fix a choice of basis. This could be a convenient choice of basis, a computational basis for your principal system, computational basis for your copy, and you just take a product basis of both of that. You perform measurement in that, okay, for each u. What you end up implementing finally is the Haar random POVM on your principal system. So this is a Haar random POVM, and this is how we choose to randomize This is how we choose to make our POVMs as random variables. Okay, now I'll come to the main result of this work. So when you converted your measurements into random variables, okay, by the way, the dimension D is fixed for this random variable. So when you converted your measurement into a random variable, your success probability also gets converted into a random variable. Okay, and you can then study how the success probability, what its behavior is like as a random variable. So we find that this probability of the success probability has this type of behavior. That is, the probability that the success probability is below some constant that is lower than what you see inside over here. On the right hand side, you have a product of two quantities. One is the dimension, and the other is exponential minus d power, exponential minus d by 12. Okay, so this probability that your success probability will be lower than this constant, that goes to 0 as the dimension climbs. Okay, you can compare this with the earlier result that you had when you did not allow for any ancillary qubits. In that case, your success probability was at most 1 by d for these type of measurements. Okay, so that would go to 0 as d tends to infinity. But in this case, you have that it does not go to 0 as d tends to infinity. On the other hand, it will at least be, it's quite with an overwhelming probability, you'll find that it will be above this constant c as the dimension keeps increasing.
Just one comment. So we have some idea what this constant is, right? So like Tanmay was using some computations using free probability theory, and it seems that it's like 1/4 this probability.
Right.
What we can prove is something like 1/10. Like this constant c. It's not like abstract mathematical constant. It's like, we give definite values for it.
Right.
Okay, but I'm a bit lost because I don't see where is this qubit? Where is this role of this ancillary qubit hidden? Where is it? Can you repeat it?
So again, we want to implement this big M, right? So how do we implement NIs, these N?
I have some problems with hearing you at the moment.
Okay.
Oh, I think we lost our speaker.
The problem is he's actually still in India, and that's just like the problem sometimes.
Okay, I saw that the connection was getting worse and worse, and I imagine that's why he disconnected.
I don't have slides, but I can like try to like while he is joining, right? Like
yes.
I can try to answer this. So it's like you have like some for this particular scheme that he described, you have some formula for the success probability, right? Like if you want to use a single qubit, you just have like some formula for the success probability of this scheme. And
but where do we get it from? This formula?
Right. So actually, the point is, so this success probability is just expressed in terms like when you analyze this protocol. He didn't give this like explicit formula, sadly, but there is given a partition that you use to simulate your POVM, you can express your success probability in terms of operator norms of those operators that you get in those partitions.
Okay, but there is some construction now of this protocol with this qubit.
So no, so the point is like in the course of the simulation, you are implementing actually a POVM that has d+1 outcomes. And sorry, I don't have slides. I can write on my computer, but like you have like I can try to improvise also on behalf of my postdoc, but like you have like d+1 outcomes. One of those outcomes is like d of those outcomes are rank 1, and one has rank like d-1 or something like that. So this specific POVM, you only need dimension 2D to implement it if you apply Nymark construction. So that's why.
Yes, but how do you make this construction? Do you write explicitly this projective measurement?
Yes, I mean this you can do using standard Nymark then.
Okay.
You know.
Yes, that's true.
Yes. Right. I'm not sure what is. So he still has problems. Right. I can.
Okay, but then how do we know that for this probability of success doesn't scale with D?
So I just in the meantime I will be talking. I will like open maybe I will be just giving some notes because like we were both involved in the work, right? So basically the key point there is that like in this simulation protocol, you have optimization over this partition, okay? So like partition that you choose when you simulate. In general, we conjecture that it's possible to that it's like the success probability would be always bounded by a constant, something like 1/4. But like we cannot prove it for all POVMs, okay? And for random POVMs that Tanmay described, you can actually get around this problem, okay? I'm not sure. I can maybe try to share a screen if you have some questions. Like, I don't have slides, unfortunately.
Okay, so now I try to understand. So you decompose your general d² outcome POVM into this subsets of d+1. Each d+1 you can implement deterministically using Nymark construction. Okay.
Yeah.
In this 2D space. Okay, so this is so the gain here is that you don't need log to D.
Exactly. Can you see my can you see my screen? Okay.
Yes.
Right. So it's okay. I was totally not in the mood for the talk. Sorry to everybody. But right. So it's like you have this general POVM that has the d² outcomes, right? And then you partition it.
Tanmay is back.
Great.
Oh, okay. Tanmay is back. Okay, so Tanmay, Michał explained a lot of things, so I think that you can try to move to the concluding part of the talk. Yes, Tanmay, can you hear us?
Yeah, sure. Can you hear me?
Yes. Okay.
Okay. So yeah, I'll share.
So please carry on, but I think that try to like converge in 5 or something minutes, or 5 to 10 minutes to the end. Okay.
Okay, sure. Okay, so I mentioned what the main result is. Okay, now also I mentioned that there is, okay, so we have a conjecture for this. After this main result, we obtain a conjecture. What is that conjecture? So the conjecture is that if you take any POVM, and there will be some partition corresponding to this POVM such that the success probability corresponding to the strategy for this particular partition that is above some constant. Okay, so to check this conjecture, we did numerical simulations. So what we did is we took 6 POVMs from dimension 2 to 323. And for each, so this is the best case simulation. Okay, so what we did is we varied over, for each POVM, each 6 POVM, we varied over different partitions and then just took the best success probability that we get for that particular partition. And then we plotted it as a function of dimension. And this is the plot that we get over here. So you see that early on, like, the success probability is large, but it starts to decrease, but asymptotically, it seems as if it converges to the point, 0.25.
So
So
sorry,
this,
so and Tanmay, so you could also plot the worst probability of success, and it would scale like 1/d, yes? Or...
So the okay, worst success probability, I don't know how that would behave for sick POVMs, but we also have mean. We also have another plot for the mean case. That is, you take a sick POVM and you take all possible partitions of it, and you plot the success probability of that, and then you take for each of these partitions, and then you take the mean. Okay, for each sick POVM, and that the behavior of that graph, it is of course below this graph, but it is it's not very much farther below. It's something like just, it's just a little bit below it. And it also goes like this.
So if I can just comment, so basically when you go to high dimensions, there are hell a lot of those partitions. So actually what we do, we don't vary, like you cannot enumerate them all. They are like, there are exponential many of them.
All right.
But in practice, what happens, random partitions seem to work pretty well. Okay.
Right.
And like, this is actually how perhaps in the future we would like to maybe prove it for like all POVMs. Like that's,
right.
And like the worst, like the best case here means like, because like in the numerics, we were drawing at random partitions. And the best case is like the best partition chosen, okay, for the simulation. So like yeah.
Right.
Yeah, and the search wasn't that hard. I mean, I think it was like maybe 50 possible combinations of indices or something like that, and it already worked well.
Yeah. All right. So actually, there's a final piece. I'll try to go through this very quickly. So, when you implement any POVM, you generally implement it with, you don't implement it ideally, you implement it with some noise. Okay, so we have two different strategies for implementing these hard random POVMs. One is, the original strategy of where you attach a d-dimensional copy to your original system, and perform random unitaries according to hard measure, and then you measure in some basis, and you end up implementing the hard random POVMs. The other is you use our like what you use the method that we propose. Okay, you attach an ancillary system and so on and so forth. So how does the noise compare? So I'll just come to the thing directly. So this quantity over here, this measures the noise.
Well,
so
I think maybe it makes sense to talk about the noise, because like it's not obvious. Sorry for that.
All right, fine. So the noise model that we use for this case is that, okay, so if our original POVM is this M, okay, the noisy version of it is just you add white noise to it. That is at the level of the POVM effects. The ith POVM effect of the noisy POVM, that is just a probabilistic mixture of the ith effect of the original POVM, okay, with just the identity matrix with a parameter, this eta, this noise parameter eta. So, and this noise parameter eta, you can write it down in terms of quantities that appear in your circuit. So you have over here minus R1 G1 minus R2 G2, so on and so forth. Okay, so R1 and so actually it's only these two guys that will be relevant. So I'll just explain these two guys. So R1 is some rate, okay, of single qubit gate errors. R2 is the rate of 2 qubit gate errors. G1 is the number of single qubit gates. G2 is the number of 2 qubit gates. Okay, so this will be relevant. The thing is that when you want to implement these hard random POVMs on your system, on your d-dimensional system, G1 and G2, the number of single qubit and 2 qubit gates, that varies quadratically with the composite system. Remember that you're performing a measurement on your composite system. The composite system in the direct NIMAC implementation was D square. And the composite system in our method is 2 times D. Okay. So, yeah, so there is a difference of the values of G1 and G2 for direct implementation via NIMAC's dilation theorem and our proposed method. Okay, so the value of this eta, this noise parameter, that also varies for NIMAC dilation and direct implementation via NIMAC dilation and our proposed method. So we have these two comparisons, so you find that this the distance between the noisy POVM and the original POVM, that is lower bounded by this quantity over here, that is 1 minus eta times 1 minus eta. So the eta subscript nk, that is the eta that you get for the Nymark dilation case, and you see that this has this form. This comes because G1 and G2 scale quadratically with the dimension of the composite system. Dimension of composite system is d squared, and hence G1, G2, they become, G1, G2, they become d square square, that is d power 4. Okay, so this is what you get. So this is going to be above that. Okay. For our proposed method, we have this. Okay, so you have that the distance, it will grow, but it grows at a slower pace. Okay, and the pace at which it's grown is bounded above by this, where c is some constant, and the eta that you see over here is the eta for the circuits for implementing our proposed method, and that scales in this form. Okay, so there is a difference between the way, I mean, so this is significant because it tells you that the noise compounding that you see in the circuits in direct Nymark implementation, they are higher than the noise compounding that you see in methods for in the method that we propose. Okay. So finally, I'll this is my last slide. I'll just come to the future directions of this work. So we want to so we have this conjecture that for any POVM there will be some partition such that the probability of success will be above some constant, and this should be true even as d increases. So we want to prove this for the worst case complexity. So this is a future direction that we'd be interested in. Then this entire thing started off with the assumption that the classical resources are free. Okay, that is randomization and post-processing, but they may not actually be free. And in fact, like speaking with Philip and Mihal, who have been working with these NISQ devices, they've seen that these things are not actually free. So what happens when you implement that more realistic model of these classical resources not being free? Okay, another future direction that we would like to consider is that, so we have seen that there is some difference between the noise compounding in direct Nymark implementation versus our proposed method. Okay, so we want to do a complexity analysis with noise along with that. So one question that I had in mind is would it be possible, okay, perhaps not, but at all, if you could sort of see some gaining of advantage somewhere with this. And finally, another future direction that you'd like to pursue is just the power of projective measurements. So you have projective measurements because you don't need to use any ancillary systems to implement them. Noise is typically a lot lower than when you have to use ancillary systems. So what is the power of these guys when you have that particular limitations? And that is a significant thing to pursue. Yeah, so this concludes my talk.
Okay, thanks a lot, Tanmay. So do we have some questions? I see Janek is chatting something.
Yes, but actually I have a general question. I really like the idea that you guys want to go with these d dimensions. I mean, this is the motivation, so I follow that, I hope. But I try to, maybe my question will be good for students, because I try to kind of figure in my head some simple case, no? And I stopped on POVM works of Michał at some stage, but I always remember this example of qubit, which you take the strain measurement, you add another projector, and it's an extremal POVM, which I cannot represent as a, I think these guys, I mean, Tanmay probably knows what I'm talking. This one is not representable by simulating it with projective measurements. No? So for such a simple example, which I think is the simplest possible, what would you do in your procedure to implement it?
So in that case, you see this type of measurement, it has 3 outcomes. So it's a qubit measurement. It's a measurement you perform on qubit. No, wait, what? It's a, wait, you said qubit rate, right? So how many outcomes does it have?
It has, oh my God, Franz, so it still has 3 outcomes, right, Michał? You there?
No, so it's a qubit measurement with 3 outcomes. Yeah.
No,
Yes,
it's a qubit.
thank you.
Okay. So it's a qubit measurement with 3 outcomes. Now, a qubit measurement with 3 outcomes, you would need an ancillary system to, these outcomes are rank 1. So you would need your ancillary system. Okay. So you would attach a single ancillary system and, you know, you don't have to do, I mean, no randomization, nothing is necessary because that is an allowed operation in this work.
Okay, but then I understood that your work applies to any POVM. You give me a system of dimension D, and you just give me a prescription how to implement it. And now I'm kind of lost.
So, okay, so one prescription to implement it is that you choose a, so you have D, okay, so you have 3 outcomes, right? So, yeah, so, you know, you can just, you just, so, okay, fine, your prescription would say that, okay, the N1, N2, those measurements are, N1 is this measurement that you are already, you know, you want to implement, and N2, you know, is, you know, it's a null measurement. Okay, so or you implement that with probably 0.
Well, probably
because you also randomize.
Wait. So if I can just, so basically our work is sort of focused on like higher dimensional case. So in this specific 1 qubit, you don't see any sort of any advantage, but assume that you would like to do, I don't know, seek POVM on a 3-dimensional system, right? Then already you will see things like, assume you want to do like, you know, those seek measurements on, you know, on 5 qubits. So then you'll need to use 6 qubits instead of 10 qubits. So you don't see it on the level of one qubit, but already from 2 qubits onwards, you will, I mean, you'll see it.
Okay. Well, it would be nice to see an example.
Okay. Any other questions? So Janek, you wanted some?
Well, there was
question?
just some 2 slides before. There was like this definition of this noisy POVM, and I understand it should sum up to identity. So I would expect the second term to be divided somehow by the numbers of
Sorry.
elements.
They should be divided. They should be divided. They should be divided by D.
Well, so then I understand it. Good.
Okay, so if there are no more questions, I don't see any raised hands or anything. Okay, then thanks a lot, and see you next week. Okay, next week. Yes, because in 2 weeks there are holidays. Okay, but next week it's normal. Okay, thank you. Bye-bye.
Thank you very much.
Thanks.